Okay, so good evening, everyone. Today we will continue with the problems which we were discussing last class. That means the internal flows of this forced convection. And today we'll also start with the problems of the free convection and also boiling. Some problems on boiling. So I will be sharing my screen now. Okay, so this is the problem of the forced convection. A a thick-walled steel pipe conductivity is given 60 watt per meter Kelvin. Carrying hot water is cooled externally by a cross flow air stream at a velocity of 20 meter per second and a temperature of 25 degrees Celsius. So the free stream velocity is given when the T infinite is also given 25 degree. The inner and outer diameters of the pipe are DI 20 millimeter and D naught 25 millimeter. So there are inner and outer diameters of the pipe. At a certain location along the pipe, the mean temperature of the water is 80 degrees Celsius. T mean, assuming the flow inside the tube is fully developed with a Reynolds number of 20,000, find the heat transfer rate to the airstream per unit pipe length. That means Q prime, which is also equal to Q by L. Per unit length you have to find out, so it is Q prime you have to find out. Now information on the inside fluid, that is water, is given, and outside fluid is surrounding fluid is air. The properties are given. Then for external flow, use the following expression Zukau's, where all the properties are evaluated at T infinity except for T towers, which is evaluated at Ts, the surface temperature. So this is for the external, that is for air. Now for internal flow, that means the water, what we have to do, first we have to find out the heat transfer coefficient for the internal flow, that is HI. Okay, so HI is given by NUI K by D. Now since it is the problem of cooling, okay, so we'll be using the Ritchie's Bolter. So the equation is HI is equal to, I'll write in the next page, HI is equal to K by DI into Nusselt number. Nusselt number is given by 0.083 D to the power of 5. So K is given as 60. Sorry, this is for the pipe. This is thermal conductivity of the solid. But for water, it is 0.67. DI, that means internal diameter is 20 millimeter, that means 0.02 into 0.023. So they already have given the Reynolds number for the inside flow. The flow inside the tube is fully developed with Reynolds number 20,000. So RED is 20,000 divided by 5 into 20 to the power 1/3. And the number is also given 2.2. So this comes out to be, so if we calculate, this comes out to be around 2765 watt per meter square Kelvin. Okay. The next is to find out what is the H naught, because for finding out this Q you require both the internal and outer heat transfer coefficient. So for finding out H naught, we'll use this equation. Already it's given H naught, just bring the K by D here. This should be D naught because it's for the outside. Then CRE, PR to the power N, PR by PRS to the power 1/4. Okay, now what is C? What is RED? What is PR? PR is given for air, right? PR is given as 0.707. PR by PRS is also given. It's almost equal to 1. Okay, now we have to find out what is C. So for finding out C and M, you need to first find out what is Reynolds number, RED. So for finding out Reynolds number, V D naught by mu. V was how much? 20 meter per second. 20 meter per second. Outer diameter is 25 millimeter, 0.025 nu. What is nu? Mu for air, right? Since it is outside fluid, 15.89 into 10 to the power minus 6. So how much it will come? 0.0314 into 10 to the power 6. That means 314. Even after this also we have 66. So it is almost, Reynolds number is this, 31466. So we just put this number here, and we also, since we know the Reynolds number now, we can calculate, we can find out the C, and also we can find out M. So this is 3 into 10 to the power 4, you can say. So this is in this range. Okay, so C is 0.26, M is 6, 0.6. K for this is 0.0263. D naught is 0.025 into RE is 31466 to the power 0.6. Prandtl number is given as 0.7. N is also given here 0.37 into this ratio is given as 1 to the power 1 by 4. So how much it comes? It comes out to be around 120 watt per meter square Kelvin. Now what is Q? Q is, since there are two heat transfer coefficient, so we'll go with the overall heat transfer coefficient, that is UA Tm minus T infinite. Now they have asked for T prime, so it should be divided by L. So we know A is pi dl, so LL will get cancelled, so it will be only pi d. Okay, if we write this, so this Q is So this Q prime is given by H naught D naught pi plus 1 by H I D I pi plus 1 by 2 pi K ln D naught by DI. This is for pipe Q for pipe, just like we have seen in conduction. So this into the temperature difference Tm minus T infinite. So if we input all the values, we will get Tm is also given, T infinite is also given, everything is given here. T infinite is around 25 and Tm is 80 degree. It's written already. So if we substitute all this value, we'll get Q prime is 489 watt per meter. So we'll move on to the next question. The next question says water at 90 Kelvin and 0.2 kg per second flows through a Teflon tube A equal to 0.35 watt per meter Kelvin. This is the thermal conductivity of the solid of inner and outer radii equal to, again this also has this cylinder also has a inner and outer diameter. So inner radii is 10 millimeter and outer radii is 13 millimeter. A thin electrical heating tape wrapped around the outer surface of the tube delivers a uniform surface heat flux of 2000 watt per meter square. So Q double prime watt per meter square, it is flux, okay, that means per unit area, while a convection coefficient of 25 watt per meter square Kelvin, that means H, is maintained on the outer surface of the tape by ambient air at 300 Kelvin, that means it is H naught. H naught is 25 watt per meter square Kelvin. And ambient air is at 300 Kelvin. What is the fraction of the power dissipated by the tape which is transferred to the water? So for this, we need to find out the Reynolds number again. Q m dot divided by pi d mu. 4 into m dot is 0.2 kg per second. Pi is 3.14. D is, since now we are finding for the for this water, right, inner one, that so we'll have to take is 10 millimeter. This is the radii, so D is diameter, so it will become 20 millimeter or 0.02 meter. Right, then mu is given as 1080 into 10 to the power minus 6. So we get this Reynolds number as 11789, which means it is turbulent inside. Fluid is turbulent. So the next thing, since it is turbulent, we can again go to the Ritz-Bolter equation, and that will be for heating. Since the heating coil is wrapped around this tube, so it is a problem of heating. So Hi is equal to K by Di into Nusselt number, which is given as 0.023 into Re to the power 4 by 5 10 to the power 0.4. Okay, so how much we get it? We put the value of K. K is obviously water because it is inner fluid. So K is this one, 0.598 divided by DI. That means this one, 0.02 into 0.023 into RE. RE we have already calculated, to the power 4 by 5, and PR to the power 0.4. PR is this, 7.56. So if we calculate all this, we'll get as HI is equal to, so this comes out to be around 2792.5 watt per meter square Kelvin. Okay, so now we know the HI. Next is to uh, find out H naught is already given, 25 watt per meter square Kelvin. So now what is given is this total flux. This is the total flux. And what is the fraction of the power dissipated by the tape which is transferred to the water? That means how much it is transferred to the water, that divided by this total flux. So how we get how much is the energy or power transferred to the water? So we know this total flux is, this is equal to H naught. This is for the outer side, above the coil or above the heating tape, and inside both conduction and convection are taking place. Okay, because of the Teflon material and also the convection inside. So this is given by TSO minus Tm. If TSO is the surface temperature of the this Teflon tube. So this is given by R naught by K Lm R naught by Ri plus R naught by Ri divided by Hi. So we know H naught, we know T infinite, we don't know Ts because the surface temperature is not given. So here from this equation we need to find out the surface temperature of the Teflon tube. Now Tm is also given 290. Okay, everything is given. R naught is given, Ri is given. This K is also given, this K. So this K is of the water, okay. So 2000, H naught is 25, TSO we don't know, T infinite is given as 300, right? TS naught minus TM 290 divided by R naught, that is 13 millimeter, 0.013. No, this is of this conduction, right? So this case of Teflon only 0.35. Divided by HI we have just found out this is 2792.5. Okay. So if we solve all this, we get TSO to be around. We know all the values, only TSO we are to find out. So TSO we get as 308.3 Kelvin. Now, how much is, so this part is the outer Q, I mean outside the coil. So this is Q naught double dash. Okay. So from here itself you can get Q naught double dash is equal to outer flux. So 25 into 308.3 minus 300. We get this as 207.5. And this part is the one which is asked in the question, that is transferred, which is transferred to the water. That means inside the Teflon tube. So how we get it? We can directly get it. This is the total Q. Suppose Q double dash. So Qi is equal to Q double dash minus Q naught dash is equal to, sorry, 2000 minus 207.5. We get this around as 1792.5 watt per meter square. So what is the ratio? Ratio between this and the power dissipated by the tape. Total power dissipated by the tape is 2000. So Qi divided by Q dash 1792.5 divided by 2000, which comes to be around roughly around 0.9. So from here the first option will be correct. Okay, then moving on to the next part. So this was all for forced convection. Now today we move to the free convection also. For this, I would like to revise some formula. So beta is compressibility factor, which is given as the reciprocal of the temperature. temperature is the mean temperature. Then Grashof number. Grashof number is defined as the ratio between buoyancy force to viscous force. So you can just go through the significance of Grashof number. Then Grashof, this ratio Grashof by the Reynolds number square. If this is less than 1, if this is greater than 1, what all it denotes, you can go through that. So if it is less than 1, it is forced, the forced convection will dominate. Less than 1 means the Reynolds number will dominate, so it is forced towards the forced convection. If it is much greater than 1, it is a free convection. And if it is almost equal to 1, then both are equally important. If it tends to be infinity, if it tends to infinity, that means this is almost negligible, 0. The denominator is 0, so it will tend to infinity. That means this is purely free convection. Okay, so next we can see some of the formulas which are used in. So for a long cylinder in free convection, we can write the Nusselt number as 0.6 plus 0.387 RAD to the power 1 by 6 1 plus 0.559 by Prandtl, this to the power 9 by 16 is whole to the power 8 by 27, and this whole to the power 2. So Nusselt number we get from here. Then from here we can calculate, obviously, the heat transfer coefficient, which is the main objective behind this studies. And also there are some relations which is given from here. Okay, this RA is the Rayleigh number. If it is greater than 10 to the power 9, then it is known as, it is the turbulent region. And of course, if it is less, then it will be the laminar. So this number is used to decide whether the flow is turbulent or laminar in case of free convection or natural convection. Just like Reynolds number decides the turbulent or laminar nature in forced convection. Then in this we get different values of C for different values, C and N for different values of this Rayleigh number. So first we have to calculate the Rayleigh number for that. Then from the table we can find out the C and also N. Then we come to the boiling. So boiling is a phase change phenomena because it changes from liquid to vapor. Uh, in boiling also we get formulas for the nuclear boiling, which is given by Rossino correlation, where Qs flux. This is also flux. This is given by mu L HFG G rho L minus rho V all to the power half into CPL into del TL divided by CSF HFG latent heat PRL to the power N. Okay, so this was given by Rosin. This is the Rosino correlation. CSF depends on this some constant empirical constant. Then for film boiling we get another equation for N Nusselt number. So this is equal to C G rho L minus rho V HFG D to the power 1/4 mu V kV, that means for vapor Ts minus T set. So all these are values are for vapor. Okay, then we can move on to the questions. The first question is, insulated steam pipe passes through a large room whose walls and ambient air are at 300 Kelvin. The pipe of 150 millimeter diameter has an emissivity of 0.85 and an outer surface temperature of 400 Kelvin. So the large room is at 300 Kelvin, that means T infinite, and the pipe, it has temperature of 400 Kelvin. Then the diameter is around 0.15 meter of this pipe. Okay, so calculate the heat loss per unit length. Again, Q prime we have to calculate per unit length from the pipe. Properties are given of the surrounding fluid, that is air. Then you can use this expression for the horizontal pipe. Okay, so here the heat loss is taking place due to convection as well as this radiation. Okay, so it is the total heat loss is the summation of both Q due to convection and Q due to radiation. Okay, so this they have already given as a hint this thing, and also the formula for this is well known. This is for convection, pi d into hd into ts minus t infinity, and for radiation the heat loss is given by epsilon into sigma ts to the power 4 t surround minus t surrounding to the power 4, where this sigma is the Stephen Boltzmann constant. Now, to start with, first we have to start for finding out the q. You need to find out the h. This for the radiation part, you know everything, but for the convection part, you need to find out the h, and for finding out h, you need to calculate the Nusselt number. Again, for Nusselt number, you have to calculate this Rayleigh number. So Rayleigh number is given by g beta ts minus t infinite into dq. This is the characteristic length. If it is, sometimes it is the length also, length of the pipe, and sometimes it is the diameter. So this is given. So g is, it's 9.8 acceleration due to gravity, 9.8, and then beta is 1 by t mean. Okay, t mean is calculated by this infinite plus this surface temperature. If you add, and the average of that will be Tm, that is 350 Kelvin. So beta will be equal to 1 by 350. Okay, and I think it's already given here. Beta is 1 by Tf is equal to 2.85. So if you calculate this, you will get around 2.857 into 10 to the power minus 3. So G is 9.8. Beta is already given 2.857. Ts is 400. T infinite is 300. Into D, diameter was given as 150 millimeter. So 0.15 meter divided by nu into alpha. Nu and alpha are given as this. Nu is 20.92 into 10 to the power minus 6, and alpha is 29.9 into 10 to the power minus 6. So if we calculate, it comes to be around 1.511 into 10 to the power 7. So for this Rayleigh number, we use this equation. So what we wrote previously, that was also the Nusselt number for this range of Rayleigh number. Rayleigh number, if you get around 10 to the power 7 and more, you have to use this. So Nusselt number is given by is equal to 0.6 plus 0.387 into Rayleigh number to the power 1 by 6, that means 1.511 into 10 to the power 7 to the power 1 by 6 divided by 1 plus 0.559. Prandtl number was given as 0.7. Now this to the power 9 by 16, again to the power 8 by 27, whole to the power 2. So if you calculate again all this, you get 31.88. Okay, now you have to calculate the HD from here. This is average. So HD you calculate as NUD into K by D. So NU was 31.88 into how much was K? It is given as 0.303 for air. It is 0.030 and diameter is 0.15. So here we calculate it around as 6.38 watt per meter square Kelvin. And if we substitute all this in this equation, Q equal to Q convection plus radiation equal to pi d HD. So it's 3.14 into D is 0.15 into HD we calculated as 6.38 into TS 400 minus 300 plus epsilon was given as 0.85 into sigma. The value of Stephen Boltzmann constant is 5.67 into 10 to the power minus 8 into 400 to the power 4 minus 300 to the power 4 bracket close. So if you calculate all this, we get the answer as 698 watt per meter. So option C is the right answer. Okay. Now next, we move to the next question. Okay, beverage in cans 150 millimeter long and 60 millimeter in diameter is initially at 27 degrees Celsius and is to be cooled by placement in a refrigerator compartment at 4 degrees Celsius. Okay, cans could be placed horizontally or vertically. So according to how it is placed, the Rayleigh number will change. That characteristic length will change, respectively having heat transfer rates as QH or QV. QH or QV. Okay. Now find the ratio between these two, QV by QH. As a first approximation, neglect heat transfer from the ends. Okay, now for vertical wall, and they have already given the Nusselt number expression for vertical wall and horizontal wall. So both of them contain Rayleigh number, of course. So first we have to find out the Rayleigh number. RAL is given by G beta Ts minus T infinite x cube divided by mu alpha. So for horizontal and vertical, the only thing which will change is this x. So we first calculate this part and keep G is 9.8 into beta is, again they have given the value of beta 3.47 into 10 to the power minus 3 into Ts minus T infinite. So Ts is the 27 degrees Celsius surface temperature of the cans, and T infinite is the refrigeration temperature, divided by mu alpha. Mu is 14.87 into 10 to the power minus 6 into alpha is 21 into 10 to the power minus 6. So if we calculate all these, we can get the Rayleigh number as 2.5 into 10 to the power 9. 2.5 into 10 to the power 9 into x cube. So for vertical surface, we can directly calculate Rayleigh number as 2.5 into 10 to the power 9. For vertical surface, x will be the length, this 0.15, 0.15 cube. So we get this around 8.44 into 10 to the power 6. Now for this vertical surface, they have given the Nusselt number HL by K equal to 0.825. We just have to copy this. Zero point 387 RAL to the power 1667 divided by 1 plus 0.492 divided by Prandtl to the power 0.563 to the power 0.296 whole to the power 2. Now if we substitute all these values, Rayleigh number and Prandtl number, what we get? Prandtl number is 0.71. For air, it is almost 0.7. So it's given 0.71. And the Rayleigh number we have already calculated here. So if we substitute all these values, we get the Nusselt number as 29.7. And then we can calculate the HL also into K divided by L. So 29.7 into K. What is the K for air? 0.0254 divided by the length is 0.15. So this comes out to be around 5.03 watt per meter square Kelvin. Now the same thing we calculate for the vertical surface, sorry, the horizontal surface. RAD here. So the x will be the diameter here. Diameter was given as 60 millimeter in diameter, so 0.06 meter, 0.06 cube, and we get this around 5.4 into 10 to the power 5. Same thing, we calculate the Nusselt number again. So the Nusselt number is equal to 0.6 plus 0.387 RAL to the power 1 by 6 divided by 1 plus 0.559 divided by 0.71 to the power 9 by 16 to the power 8 by 27 whole square. So if we substitute the value of RA and okay, this was PR. I wrote P. Sorry for the interruption. So if we substitute all the values of this RA, Rayleigh number and all, so we get the Nusselt number as 12.24, and from here we get HL is, so this will be HD because it is horizontal, so HD is equal to ND into K by D. Okay, so 12.24 into K 0.0254 divided by D is 0.06. So this comes to be around 5.18 watt per meter square Kelvin. Okay. Now we were asked to find out QV by QH, that means vertical by horizontal. So if we see Q Q is equal to H HA delta T, right? So HA is pi dl delta T, Ts minus T infinite. Okay. So for QV, this will be For QV, this will be HV. For Q horizontal, this will be H horizontal. So the only thing different varying here is this H. Others all are same. Ts minus T infinite is constant. I mean, it's the same for both. And area also doesn't change. It's the same for both. So what we have to calculate is QV by QH is equal to HL by HD. So it's 5.03 divided by 5.18. It comes to be around 0.97. So next is this is the next question. Determine the average convection heat transfer coefficient for the 2.5 meter high vertical walls of a home having respective interior air and wall surface temperatures of 20 and 10 degrees Celsius. Okay, so it's a uh, surface structure of four walls. Okay, I mean it's like a home. So the height is around 2.5 meter high vertical walls of a home having respective interior air and wall surface temperatures. So the air temperature T infinite is 20 degrees Celsius and surface temperature, that means the temperature of the walls, is 10 degrees Celsius. This is the length. Okay. Then what we have to find out? We have to find out the average convection heat transfer coefficient. That means HL bar. Okay. So this is what we need to find out. This whatever was the previous question formula. So this was for vertical, right? This is for horizontal. So since the next question is they have asked for the vertical walls, so we have to follow this equation. Okay, so we find out NUL is given by 0.825 plus 0.387 into RAL to the power 0.1667 divided by 1 plus 0.492 divided by Prandtl number to the power 0.563 whole to the power 0.296 whole to the power 2. So this is the Nusselt number. So we have to, for that we need to calculate this Rayleigh number first. So Rayleigh number is calculated by G beta Ts minus T infinite L cube. L here is 2.5 meter. Then mu. So G is 9.8. Beta is given 3.472. Ts is given 10 degree. T infinite is 20. So Ts minus T infinite, or you can write T infinite minus Ts also, depending. It's just the temperature difference. And the nu is given as this 14.82 into 10 to the power minus 6 meters square per Kelvin, sorry, per second. And alpha is given as 20.9 into 10 to the power minus 6 meters square per second. Okay, so if we substitute all the values in this Rayleigh number, we get the Rayleigh number is 1.7 into 10 to the power 10. Okay, it's very high Reynolds Rayleigh number. So we substitute this value in this equation, Nusselt number equation, and also we substitute the value of Prandtl number here, and then we can calculate it as around 299.6. It comes up to be around 299.6. Now we calculate the H bar from there, the average heat transfer coefficient, which is exactly what asked in the question. So NUL into K by L. So 299.6 into K is 0.0253. So this is the conductivity of air, almost 0.025. Then length is 2.5. This comes out to be around 3.03 watt per meter square Kelvin. So D is the right answer here. Simple. Now next question. So this question says saturated ethylene glycol at 1 atmosphere is heated by a horizontal chromium plated surface which has a diameter of 200 millimeter. So the diameter is given here and is maintained at 480. That means the surface temperature is 480 Kelvin. Estimate the heating power requirement and the rate of evaporation. Heating power, that means Q, you need to find out. Flux also you can say, because power is anyway energy by area. And also the rate of evaporation, that means m dot. Now at 470 Kelvin, properties of saturated liquid are, the properties are given at 470 Kelvin. The dynamic viscosity is 0.38 10 to the power minus 3 Newton second per meter square. Cp is given, Prandtl number is given, specific heat and Prandtl number. And same for saturated vapor also it's given. The density is given 1.66 kg per meter cube. Now assume nucleate boiling constant. This is the constant CSF is equal to 0.01 and N is equal to 1.0, that means 1. So all these terms you get in this equation. This is for boiling, right? Nucleate boiling. Now the saturated properties are given for the materials, that means saturated ethylene glycol at 1 atmosphere. Saturated temperature is 470 Kelvin. HFG is given as 812 kilojoule per kg. The density is given as 1111 kg per meter cube. and the surface tension is given as 32.7 into 10 to the power minus 3 Newton per meter. So for boiling, we use this equation. They have already given which correlation to use. Okay, so directly we substitute all the values. So Qs is equal to mu L. Mu L is given as this saturated liquid, right? So 0.38 into 10 to the power minus 3 HFG, latent heat 812 kilojoules. So converting into joule, 10 cube joule per kg into again 9.8 into rho L. Rho L is this given as this. The liquid is a ethylene glycol, right? So the rho is given as this 1111 minus rho V. Rho V is also given. The saturated vapor density is 1.6666 divided by the surface tension 32.7 into 10 to the power minus 3 whole to the power half into CPL. That means this 3280 into delta TE. Delta T is the temperature difference. So the temperature difference, the surface temperature is 480 and 470 is the saturation temperature. It's given here. So 480 minus 470 is the delta T. Then CSF is given here 0.01 into HFG is 812 into 10 to the power 3 into Prandtl number to the power n. Prandtl number is given as 8.7 to the power n is 1. So now if we calculate this whole thing, we get this. If we calculate this whole thing, we get around 1.78 into 10 to the power 4 watt per meter square. Heating power requirement. But the option here it gives power is energy by time. So the answer we got is the flux. Okay, that means per unit area. So we need to just multiply it with the area. Okay, then we get how much is the Q boil. So Q boil is equal to Q double dash into area. How much is the surface area? So they have given only diameter, nothing else they have given. So we can consider it as a cross section. So area will be given by Q double dash into pi d square by 4. Right? Now Q double dash was 1.78 into 10 to the power 4 into 3.14 into d is 0.2 meter divided by 4. This comes out to be so this will be 0.04 divided by 4 will be 0.01 0.01 into 3.14 into 1.78 into 10 to the power 4. So it comes to be 558.9. So which is the option? It will be the first option, 560 watt. Okay. Next is to find out the m dot, right? So for finding out m dot in terms of, we also know that Q is equal to m dot into HFG. So m dot is equal to Q by HFG. So 558.9 divided by HFG is 812 into 10 to the power 3. So this comes out to be around 6.89 into 10 power minus 4 kg by second. So 6.89 into 10 to the power 4 kg by s. So this is the m dot. Okay. So now we move to the next question. An electrical heater in the form of a horizontal disc of 400 millimeter diameter is used to heat the bottom of a tank filled with engine oil. So this is filled with engine oil at a temperature of 5 degrees. So this is used to heat this oil at a temperature of 5 degrees. This is the heater. This is the heater in the form of horizontal disc. This is the heater. The whole one is the heater. 400 millimeter diameter is used to heat the bottom of tank filled with engine oil at a temperature of 5 degrees. So this is the oil which is at 5 degrees Celsius. Now what will be the power required? The power required to maintain the heater surface temperature at 70 degree. Now this surface should be maintained at 70 degree. Now use the following data. Engine oil at TF is given as T infinite plus TS divided by 2. This you know. Then viscosity is given, conductivity is given, diffusivity, and beta. They have also given this relation for RA, Rayleigh number 10 to the power 4 to 10 to the power 7. You have to use this relation. For Rayleigh number from 10 to the power 7 to 10 to the power 11, should use this relation. Assume that the oil is quiescent and that the system is at quasi steady state. Use the following information as needed. This. So it is quiescent, that means it is steady, it is not moving. Okay. Then, so what is the power required to maintain the heater surface temperature? So first, we have to calculate the Rayleigh number, right? So for calculating the Rayleigh number, we have G beta Ts minus T infinite. Diameter is given, so diameter d cube nu alpha. So G is 9.8 into beta is 0.7 into 10 to the power minus 3 into Ts minus T infinite, surface temperature is 70, oil temperature is 5 degree, into d cube. D is 0.4, 400 millimeter is 0.4 meter, nu is 288 into 10 to the power minus 6 into alpha, right? 0.847 into 10 to the power minus 7. All are in SI units, so you don't need to change anything. So if you calculate this, it comes out to be around 1.828 into 10 to the power 7. So since it is in this range, we'll use this relation, right? 1.828 into 10 to the power 7. So it's greater than 10 to the power 7, right? So NUL, you can write NUD also, anything. NUL HD by K is given as 0.15 RA. R is 1.828 into 10 to the power 7. To the power 1 by 3, right? So if we can, how much it comes? It will come out as 39.5. So from here we can calculate what is this H. H will be 39.5 into K. How much was K? 0.145 divided by D. That means 0.4. So how much it comes? Comes out to be 39.5 into 0.145 divided by 0.4. Sorry, this is 39. Okay, one thing here was while calculating this D is calculated this it is calculated using area by perimeter. So this comes out to be area is pi d square by 4 divided by perimeter. Perimeter is pi d only. So pi and pi cancels. D and D cancels. So it is D by 4. Okay. So this becomes this characteristic length becomes 0.1. Okay. So in the same way, in this also, this is also the characteristic length. So this will be 0.1. So it comes 5.7 divided by 0.1. That is 57.27. Okay, this is watt per meter square Kelvin. Now what we were asked to find out, we are asked to find out the power, how much power is that means Q. Okay, Q we can find out since we got the H, we can find out Q. For Q, ES delta T, H is 57.27 into ES pi d square by 4 only into Ts minus T infinite 70 minus 5. This will come out to be around 468 watt. Okay, so this is the power requirement to maintain the heat surface temperature at 70 degrees Celsius. Now we'll move to the next question. Estimate the nucleate pool boiling heat transfer coefficient for water boiling at atmospheric pressure on the outer surface of a platinum plated 10 millimeter diameter tube maintained 10 degrees Celsius above the saturation temperature. So now comes the phase change problem. There is a boiling, pool boiling, nuclear pool boiling. So for this, we use the Rosenau equation. So what was that? Q was equal to for nuclear pool boiling, we use that equation. Q is equal to mu L HFG G into rho L minus rho V divided by sigma to the power half into CPL into delta TE divided by CSF into HFG into PRL to the power N whole to the power 3. Let me just check it. Yes, so this was the equation, Rosenau correlation. Now what we were asked to find, estimate the heat transfer coefficient. So this is the equation for the heat rate. This is the equation for the heat rate, but we need to find out the heat transfer coefficient. So we know H delta T only. So just divide this Q by delta T, then you get the H, right? So now for this, how much is the, I'm directly writing the answer, please calculate it. Just insert all the values. Mu L will be 279 into 10 to the power minus 6. Then HFG is this 2022 557, sorry, 2257 kilojoule. So you have to multiply with 10 cube to get this in joule. Then G is 9.8, rho L is, so if I write all this along with this delta E, we can write as 279.10 to the power minus 6 into 2257 into 10 cube divided by this delta E. Delta TE is maintain 10 degree above the saturation temperature. So already they have given as a gradient temperature, so it is 10. Then G is 9.8 into rho L. Rho L is this 957.9 minus rho V is 0.5955 divided by surface tension is 58.9 into 10 to the power minus 3 whole to the power half into CPL. 4217 into delta T is 10. CSF is given as 0.013 into HFG 2257 into 10 cube into Prandtl number to the power n is 1 again. So Prandtl number is 1.76 is whole to the power 3. So if you calculate this whole thing, you get the answer as 13685 watt per meter square Kelvin. So this is the answer. Okay, we'll move to the next question. Copper tubes 25 millimeter in diameter and 0.75 millimeter long are used to boil saturated water at 1 atmosphere. If the tubes are operated at 75% of the critical heat flux, 1.26. So operation 1.26 megawatt, right? So if you call this as QC double prime because it is flux 1.26 into 10 to the power 6 watt per meter square. So operating flux will be 75% of this, that means 0.75 into 1.26 into 10 to the power 6. Alright, how much you get? You get this to be around 9.45 into 10 to the power 5 watt per meter square. Okay, so next, if what they have asked to find out how many tubes are needed to provide a vapor production rate of 750 kg per hour. So if you want to find out the number of tubes, we can calculate it by, we know that this production rate into HFG also gives the heat rate, but that is the heat rate, I mean the total heat rate. So this divided by how much the the operating rate is, the operating flux. This is the flux. So if you want to find out the rate, you have to multiply it with the area. So area is, since they are tubes, so they're cylindrical in nature, should be pi dl. So what does this mean? So if you are to provide a vapor production rate, so this should be the requirement. This is the requirement, and how much each one of them are giving, if the tubes are, I mean they're operating, so this, that is given by this. So this will give you the number of tubes. So m dot is already given 750 kg per hour. And you can convert this into seconds also. Per second it will be divided by 3600. Okay, then HFG given as is 2257 into 10 cube divided by Q double prime is 9.45 into 10 to the power 5 into 5, 2.14, 0.75 is the length and diameter is 0.025. So how much you get this? 845 into 10 to the power minus 2. So it will be 8.45. So since the number of tubes cannot be in fraction, you have to take, the bigger number. So it should be rounded to 9. So minimum requirement is 9. You cannot go below that. Okay. So that is what it means. So the number of tubes we have calculated as 9. Then and the next question is, what is the corresponding tube surface temperature? That means Ts. So this is a situation of boiling only, used to boil saturated water. So again here we use the Rosenau equation. Rosenau equation will give mu L H F G rho L minus rho V divided by sigma to the power half CPL into delta T E CSF into HFG into Prandtl number to the power n whole to the power 3. So you have to calculate the surface temperature. So from here, this TE we can also write as TS minus T infinite. So here, what is the T infinite? That is the saturated water only. Okay, that is used to boil. So T infinite, you can also write it as, or you can directly find out what is the delta T from here. Instead of this, you can write as delta T. Delta T only you can mention. So from here, delta T, how will you find out? So it should be mu L HFG PS will be there in the front, and this will become whole to the power basically Q is divided by all of this. So we can directly write as Then this equal remains the C plus HFC to the power n L3. So this whole to the power one third will become right. So this is how you calculate the delta T. Then from here, how do you calculate the the tube surface temperature? Now, if we substitute all the values, Qs you know already, Qs is this, and other values also we know, mu L, HFG, everything is given, rho L and all. So if we substitute all this, we get delta T as 19 degrees Celsius. And how much is the, here I said that T infinite is will be the temperature of the water, but the water is saturated water. So the temperature is given already. Delta T is this. So delta T is equal to Ts minus, instead of T infinite, you can write saturated is equal to 19. Okay, so Ts will be saturated temperature of water is 100 plus 19 will give us 119 degrees Celsius. Alright, so this is how we calculate the temperature. So just you need to, since it is a very big formula or correlation, so you can, if you want to calculate this, you can directly put everything else under this, and since it was cube, so if we go to the other side, it will become 1/3. So we can just calculate like this direct. Then delta T we can find out from here. Okay, then we'll move to the next question. The electric current passes through a horizontal 2 mm diameter conductor of emissivity epsilon 0.5 when immersed in water under atmospheric pressure. Estimate the power dissipation per unit length of the conductor required to maintain the surface temperature of 555 degrees Celsius. So here this problem is the case of fin pool boiling. So the previous one was nuclear pool boiling. That's why I use the Rosenau equation. But here we use another equation which is for the pool boiling. So for pool boiling, the equation is something else. Okay, so here we start with what they have asked to find out, estimate the power dissipation per unit length. That means Q prime. Q prime they have asked. Okay, required to maintain the surface temperature is 555 degrees Celsius. T set is also given 100 degrees Celsius. So Q prime is equal to, we know Q is equal to HA delta T, but here it won't be, or instead of A we can write A by L because it is prime means per unit length, delta T. Delta T is Ts minus T set. Okay, Ts is the surface temperature, T set is the saturation temperature of water. So HA is pi dl only. Okay, cylinder. Most of the problems are of cylinder only. So L will get cancelled. So basically we need to find out this. So for this first thing, we need to find out H. And for H they have given this relations. And to find out this H, what we have to do for full boiling, Nusselt number is given by C, sorry, C or else we can directly write what is the H. H is Nusselt number into K divided by D. So H is equal to Kv by D into C. So from here starts the Nusselt number from C. So G into rho L minus rho V into HFG prime D cube divided by V EKV delta TE whole to the power 1 by 4. So what is KV? KV is the vapor conductivity 0.0929 divided by D is the diameter 2 millimeters, so 2 is 0.002. C is given 0.62. G is 9.8 into rho L minus rho V. Rho L is 957.9. I'm directly writing the uh, difference since I don't have much space. 957.9 minus this and this 72.99 is equal to 8. Directly writing this whole value 884.91 into HFG prime. So this is given by HFG plus 0.8 CPV into TS minus T set. So for this, we again need to find out what is this HFG is here. Okay, we have to calculate all this first. Okay, so better we calculate that. HFG prime is given by HFG plus 0.8 CPV TS minus T set. So HFG is 2257 plus 0.8 CPV. Means for vapor we need to find CP is very CP this one 88750 into TS minus T set, that means 555 minus 100. So we get some value here. Okay, that value we put here, and then this VV is for, this is new V actually. So this you can just calculate by this mu divided by rho will give mu, then kv is this, then delta t is again ts minus t set. So all these values, we just substitute all these values and we get how much is the h. All right, then we get the h to be around, if we substitute the values of h, the values of those parameters, we get H as 2108 watt per meter square Kelvin. So after that, we see this is for convection. For radiation, we calculate as epsilon sigma Ts to the power 4 minus Ts surrounding, or sorry, this is saturation to the power 4 divided by, so this is Q, this is Q radiation. So if we want to find the H, just divide by the delta T. Okay, this will be around 28 watt per meter square Kelvin. So if we get this, so what we get from here, see from here, in the question is already given if the radiation heat transfer coefficient is less than the convective heat transfer coefficient, that means this already we can see, then you have to use this relation. So this is already lesser than this, it's 0. Okay, H red is lesser than H convective. So we have to use this formula for finding out the H. So H is equal to, H bar is equal to H convection plus 3 by 4 H radiation. So we calculate it, 2108 plus 3 by 4 into 28, 721. So almost we get like this, right, for H. Now we have to find out this Q. So H pi d into Ts minus T set. H pi d Ts minus T set. So H is 2129 into 3.14 into D is 0.002 into Ts is 555 minus 100. How much is it coming? 2129 into 3.14, 6083. So it is 6083 watt per meter. So you can also say this as 6.08 kilowatt per meter. So this is the answer for this question. Right, just substitute, you just need to substitute the values here in whatever, you just need to know what correlation to use when. Okay, so thank you for today. We'll continue in the next class.